My heritage is more New York to me.
There you go.
Right. I'm sure your being Armenian, I'm sure your heritage is more Glendale.
Right. No, but yeah, that's a good point. You're identifying with New York. I'm LA. I'm born and raised in Los Angeles. I identify with Americans.
Right.
But my culture
is
yeah, it's very good. Thank you for that. I appreciate it.
No, totally. All right, so we do have a guest today, and he's going to school us in some things. And this is going to be not a response so much as a continuation of a discussion we had last quarter when we had Hilda on to discuss time and how we experience time. And that's, as philosophers, that's how we mostly care about it, is the experience, or as she put it, the phenomenology, which is the big word in philosophy and even in science for how we experience things versus how things are. And today we're going to have on a scientist, so he's going to school us basically in how the brain actually works, and hopefully Robert and I will not be too left behind in the conversation. So do you want to introduce yourself?
That sounds very fancy, calling me a scientist. I don't think I've ever been introduced like that for anything.
You work with a, what is it? It's called a PI, right? It's not a private investigator.
Principal investigator, yeah.
Principal investigator. So you are actually in the lab doing things, right?
Yes.
Good enough
I'm
for
not
me.
in the lab anymore.
Oh, well, you're an ex-scientist.
Yeah.
Did you get fired? Were you stealing beakers?
A soon-to-be neuroscientist, as soon as I get that degree in the mail.
Right. All right, so I'm going to call you a scientist in training then. How's that?
Sounds good to me.
Sounds great to me, too, because that's what I was supposed to be until I went the philosophy route. So you're doing the thing I couldn't do, which is being in the lab and getting the information that eventually I will try to make a career off just talking about. So first of all, let's talk about what we were discussing philosophically. And did you give your name? I want to make sure you give your name.
My name is Joel Yancey.
And your major and your year and all that good stuff.
Neuroscience major, bioinformatics minor.
Yeah, big, huge words. We're going to talk about that.
This quarter.
So,
and,
yeah. But you graduated already. You said quote. I'm doing air quotes.
Yeah,
graduated. You commenced.
Yeah, you know that routine.
Yeah, we do the walk before we actually graduate. That's how fast UCLA wants to kick us out of the building.
You think UCLA will notice if I walk again?
I actually don't think so, Joel. I really don't think. With all those students,
they probably noticed that
I just walked in.
Well, don't they call your name? Do they call your name?
No, not for the big one.
Oh, they don't.
There's departmental, which are the small ones.
Just fucking go. Yeah. Just fucking do it again.
Yeah, you should just go and be like, I sat in this spot the second time. I sat over there the third time I did this, the fourth time I did this.
Yeah, I want to get front row this
just
time.
Keep coming back.
Well, do you guys know who the speaker is this year?
You mean like the keynote speaker?
The keynote speaker,
no.
Yeah.
Do you?
I don't know.
Oh, I thought you were going to tell us.
Yeah.
It should be released, though.
No,
I'll look it up right now, though.
It was like a surprise. I thought we were like, who is it going to be? Is it going to be Howard Stern? That would be great.
No, I don't think it's anyone that cool. I think it's it's some businessman, I believe, if I remember reading. Because I remember reading about it, so I knew, but I didn't remember it, so obviously it wasn't anyone I care about. Some businessman who went to UCLA, probably made a lot of money, and because the United States' actual religion is capitalism, he's a prophet now. So he's probably going to tell us how to go make that money. Anyways.
Dead money.
Exactly.
I think you might be thinking of the guy that was the commencement speaker last year.
Really? Well, that's neither here nor there. That's not part of the topic anyway. So, Robert, what do you remember about the last episode we had about talking about time?
Well, I remember having the time of my life in Chicago.
Robert with a pun. Let's go. You're lucky you're in the other booth. I'd smack you in the face.
I know. I had to get that in there.
That's what she said.
I wasn't here, and I distinctly remember you insulting me for being in Chicago. So
that's right. You weren't here for that episode.
I wasn't, but I did edit it. So I listened. I did listen to it. I just would.
You were blaspheming with the Chicago pizza.
Right. Oh, amazing.
You bastard.
Amazing. But look, I don't know enough about that. It seemed like she was arguing that you cannot account. Excuse me. Scientifically, you can't account for somebody's qualitative experience of something. Mm-hmm. But I don't know enough about this subject matter to really go off on it. So I would like Joel to kind of take us through it.
Joel, were there any specific points you wanted to talk to about the last episode? You said you wanted to talk about qualia, right?
Sure.
All right. So qualia, as far as I know about it, and hopefully I'm not butchering it too much, is the distinction between objective reality and our subjective experience of reality. So we as scientists, yeah, right, like I'm a scientist. So we would just say there's like all these colors around us, and every one of those colors is a specific frequency of light, which it is, and we can measure that, and we can predict all types of properties from it, because quantum mechanics is pretty much the greatest theory we have in science. And so that red I'm seeing on the door is a specific frequency that will be interacting with my neurons or rods and cones and other neurons in my eyes. and they will be affecting all these types of things in very specific ways, and then sending signals in very specific ways down my the nerves from my eyes. Oh God, the nerves going from the back of the eyes just flew out of my head. The names for these friggin' structures, but you know what I'm talking about. The occipital lobe goes to the occipital lobe, and suddenly I see something. I experience that. Qualia comes from the other direction about basically what our mind's eye sees. Like, what is the color red? You can't explain what the color red is in some type of terms of numbers. I mean, this goes a lot of philosophy, which is kind of subtle and kind of silly, but also kind of deep, is called the pothead philosophy. Not officially, but it's basically, dude, what if my red is like your green? Right? That type of pothead type of philosophy. And that's basically what qualia gets to in a more serious way.
Can I jump in?
Yeah,
on
go
that
ahead.
Point?
Of course.
So when that point is made, when color is brought up and people seem to get baffled by color, and that's understandable, color is just an internal label. You know, light hits our retina, our photoreceptors encode the information, you know, depending on what color the light was, photoreceptors become activated. And that sends a signal to downstream neurons in the brain, eventually reaching the cortex, upstream neurons, I should say, eventually reaching the cortex for processing. But that's just like every other sense. That's just like the sense of, you know, touch, smell, hearing. You've got sensory-receptor neurons. That's always step one. And then that signal gets passed along until it reaches the cortex for processing. It's the same. Are you making a different point? This is my question. By talking about color as opposed to saying, what's the point about color?
The point about color is that you can't go from any scientific theory, supposedly. This is one of the things you can refute, that says, you know, red is 500 nanometers, and I'm probably getting that backwards. I always mixed up the numbers. That's what cheat sheets are for. But say if light is 500 nanometers, you know, wavelength, you can't say 500 nanometers is going to be, in my mind, this specific hue or not, I don't want to just repeat the word color, but you know what I'm saying, like shade, right? So like what, in other words, could it have been, maybe it is in Robert's mind that what the object I experience is red, he sees as the color green. Like, is it possible that we're experiencing these things a different way? And I think the thing that messes up scientists on this, so it's one of those things that's not verifiable,
but a color is
right?
not something that's out there in the world. A color is an internal label. It's it's the state of encoding a bit of information from the external world in your cortex.
Sure.
That's all a color is.
But it isn't. But it is an experience.
So when
right?
you say does one person experience green, or could one person experience green the way somebody else experiences red, that just because that question can be asked doesn't mean it's a valid question. I don't think.
That's true.
So.
Well, I think the point of it is to go beyond the colors, and that's just an example. Like emotions is another one, and even thought could be another one, right? And I think that's what we were talking about in the last episode, is how could we have phenomenological experiences when, if supposedly as a reductionist like myself would just say, we're just neurons, right? We're just electrical impulses around neurons. You know, how do you jump that gap from a neuron to us having this conversation or experiencing this conversation? Well, one more thing before we get onto that, I do want to say something else.
Before we get onto consciousness?
Yeah, right. Before we get to that huge topic, I want to show you one picture. And I invite everyone at home to do it, is if you just go on any screen like your phone or your computer, just type in the word yellow into Google and look at this square there. I mean, you're experiencing that square as yellow, right? But there's not a single thing on this screen that is yellow. There's nothing that is that frequency. It literally does not exist in the real world because this is an RGB monitor. So
I'm struggling to understand your confusion, though. I mean, like, sound is just pressure waves in the air that reaches the sensory neurons in your inner ear that encode that information, and it's just the same thing with colors. So why isn't your confusion related to the pressure waves that are detected by the hair cells of the inner ear?
I'm not too sure it's confusion on my part so much as a...
No, it's my failure to understand where you're coming from, and I'd like to understand what is the specific confusion with color. I mean, because...
I think the
light
point is
out
how
there.
do we...
Color isn't out there, but light is out there, and there's different types of light. Light
can
have different
like I said,
wavelengths, so that's an objective thing that's out there.
If I hand you a yellow piece of paper, like there's a certain frequency coming off that, right? And this is why I'm bringing up this example.
Yeah.
That frequency is not coming off this monitor, but I'm experiencing the exact same color. So there has to be something else on top of the sensory information we're getting that is making me feel like I'm seeing this specific color.
Why?
Well, because just like we said, the frequency that comes off the paper is not present here, but I'm seeing the exact same thing. You see what I mean?
The frequency is different.
Yeah.
So that's an objective difference. That's in
But
the
I'm not
external
seeing a
world.
difference. So I'm seeing 2 different frequencies, or in this case, 3 different frequencies from the one on the paper, but I'm experiencing the exact same color sensation.
Right. I mean, like, you've just imagine different types of photoreceptors. You got 3 different types of photoreceptors, well, 4 types, but 3 types that are encoding color. And the different relative amount of activation that each of those photoreceptors get for a specific wavelength of light, that's a different signal that the brain can interpret and just label as a specific color. Like, when these photoreceptors are firing this much and these photoreceptors are firing this much, that's a blue that you're detecting.
Are you
We're going in circles here.
Yeah, well, a little bit.
Yeah,
Let me
okay,
give you another
keep
example of a study I find interesting. And I'm sorry I don't have the exact citation for it, but I'll try to provide that later. Basically, it's been discovered that if a culture has more words for a given shade of a color,
I've heard this.
then they can see more shades of that color.
Yeah.
So if I present some person, let's say culture A has 10 words for red, and my culture has 1
I feel
word
like
for red.
reporting could come into play with it.
That's probably true. Let me explain the full thing. So basically, this culture B, with their many words, you can give them 10 different pictures that are all different shades of red, and they'd be able to identify all of them. This is red 1, red 2, whatever you want to call them, crimson, maroon, whatever.
Right.
But because I come from a culture that just lumps all those shades into one color, I literally, physically, would not be able to make a distinction between those samples. They would look identical to me.
So your qualitative experience would be that maroon, let's say, like darker red to us, would be the same as scarlet.
Yeah, I wouldn't be able to
it was
actually
just like
make
it
the
looks
physical
the
distinction.
same.
Yeah.
Oh wow.
What
Okay.
do you think about that, Joel?
I'd have to read the study
Sure.
and see how. I have heard of that study, but yeah, I don't know.
I remember the way it was discovered, supposedly,
It just seems
was
like that
actually
would be a
by
different
accident.
study to carry out.
Yeah.
A lot of sources of error.
That
So-
is interesting though that they would lump different shades like that because their brain has accepted the linguistic these are different terms for different colors.
Yeah.
So they haven't. So
The
they just lump it
philosophical
in.
implications are huge.
Yeah.
Because then you can try, if that is true, you could try to say, maybe apply it to social sciences where maybe there are people who are against, LGBTQ type people because they are only trained to see male and female, and maybe the
Yeah.
brain is working similar there. So there's a lot of ways you can approach this. And so it's actually a pretty interesting topic. But Joel, you don't have any immediate intuitions to that, maybe, like what could be happening? Not to put you on the spot or anything. But
I'll let you know if I think of anything.
That's fine. So that's basically what we were talking about last time. The phenomenological, of course, we were talking about color. I should have transitioned into time. So basically, we're talking about how do we experience time? Is it this many slices of reality we're experiencing one after the other? Or is it more of a time is a specific... I remember Hilda explaining something like pages in a book. If you remember that, Robert?
Yeah, when she's talking about the B series
Yeah.
and the A series and the different series, I didn't really want to respond directly to that point.
That's fine.
I'd rather just give kind of like my analysis of where the field is at in terms of what neuroscience has to say about.
Yeah, that's what I was getting to. Now, going off of time, I want to get directly into your research. Do you want to give a brief introduction of what you do and like what the lab's purpose is and stuff like that first?
Yeah, so I worked in the lab of Dr. Dean Buonamano here at UCLA for 3 years, and we worked on it was a joint project with the Blair Lab down in the basement of Franz. And what we did was, this was a in vivo electrophysiology experiment. So we were dealing with live rats, and we had implanted electrodes, tetrodes specifically, in their auditory cortex.
Tetrodes?
Yeah, so a tetrode is just 4 electrodes wound together. It doesn't matter. But we're recording extracellularly, so we're in their brains and we're recording from their neurons. We're detecting the electrical signals being sent off by these neurons from outside of them. And so we spent a while acquiring a lot of data on what these neurons were doing in the brains of these rats. So we had 2 different experiments that we ran. The first one is we played auditory tones of different frequencies to them, while we're recording their brain activity, the response to those different frequency tones. So we'd have a low-pitch tone, a high-pitch tone, and noise, which is all of the frequencies. Basically, that was the simple, easy experiment. We just wanted to see if after acquiring a lot of that response data, if we could predict basically without knowing beforehand what tone was played, if we could look at the brain data from one trial and say this tone was played. So that's we can call that spatial processing.
Were you able to do that?
We were able to do that, yeah, very well. And that's spatial processing. And spatial processing is the way that all of our senses basically work. When you touch something, when you smell something, specific receptors are being activated. That's activating specific neurons down the line. So basically, it's a one-to-one correspondence there. But a more interesting question is, how could the brain, in theory, encode intervals of time? And we know that it has to be able to do that because if, let's say I just played we don't have to actually do it. Let's say I played a high-pitched tone and a low-pitched tone separated by 100 milliseconds. You'd be able to tell me easily which one came first and which one came second. So you know the order of the tones. There's temporal information in that. Or if I just, played two different intervals, tones at different intervals, you could tell me which one was longer, which one was shorter. So we know that the brain is encoding these different intervals of time. But how is it doing that? Because that's a trickier question to answer. Because you can't see how that could be done. Just think of any other sense. Smell, specific receptors detect different smells in the air, activates a specific subpopulation of neurons. With vision, specific photoreceptors are being activated. Do you see what I mean? Is that clear?
Yeah. Robert,
right,
you getting that too?
Totally. I understand everything. No, I'm listening. So please continue.
So that's a trickier question, and neuroscience doesn't have an answer for that yet. How can intervals of time be encoded? But we know that the brain has to have a way of doing that. And so one possible explanation could be that the brain has a central clock. You can sort of see where that clock is at and refer to that clock and get a measure of time. I'm not sure what that would look like in terms of, or how that would translate into neural circuitry. It's a little bit more difficult to imagine. But another way we can imagine that happens is just through the dynamics of the neural population. And so I'm sure I lost everyone there, and I'll get back to that. But I'll just finish explaining my research. So that's a trickier question. So
your experiment was designed to try to answer that question, all right?
Yeah.
Okay.
But we weren't guaranteed to get good results there, so we wanted to have some results, and this was my independent research project. So we also did the more simple experiment, which was just, can we just acquire enough data from the auditory cortex to predict which tone was played? But so the way we run the more interesting experiment is we play different tone orders. So we'll play a low pitch, then a high pitch, low pitch noise. There's 3 different tones, so there's 9 different permutations there. And basically, we look at the activity of the neurons. Is this clear?
Yeah, I'm following
along. Are you guys
along.
following me? Okay.
Yeah.
So just imagine that we have 2 tones played. They're different tones. And after the second tone, we're looking at the activity of a population of neurons. And if we can use some algorithms to learn a lot about how these neurons work. This is where actually machine learning comes into play. We used SVM algorithms to do this. Basically, we're just trying to see if there's information in the brain activity after the second tone about the first tone. And if we can do that, then we can basically say that there's information in this population of neurons. It sounds weird to say, but that is what I mean to say. That there's information in this population of neurons that's temporal.
Let me see if I'm following. So, first of all, basically, you have this readout, obviously, that's showing you some type of graph. Let's just get really basic, right? And this is the activity of some neurons. And when you play a certain tone, that graph will have a certain shape. Is that correct so far? As opposed to a different tone?
Well, we acquired a lot of data, and then we analyzed it and at a very later point in time. So this isn't live,
No, I mean, that's fine.
We acquired a lot of data.
But I was looking at your poster there, and it seemed that what it was. You looked to me like you had this graph that says this is kind of the neural activity.
I see your confusion. Those weren't individual neuron spikes that we were saying on there, which is what you thought they were, right?
Yeah, maybe.
Yeah, no, they weren't. Those are called PSTHs, peristimulus time histograms.
Okay.
And it's just over, I think it was 100 trials. You just add up all the spikes and you bin the data, and then you plot that, and then you just fit like a Gaussian fit to it. And then, that's why it's smooth. But it's just like binned spike data. So how many spikes? And when I say a spike, I mean a neuron firing. How many spikes were there in this time bin over the course of those 100 trials?
I see. So when you play a specific tone, you're measuring which neurons fire more than the others?
Well, we're looking at the response of the neurons. Sorry, ask your question again.
I'm just curious exactly what you're measuring when you play the tone. So you said you can tell from some type of data whether they heard a high-pitched tone or a low-pitched tone. What exactly are you measuring?
We're measuring the brain activity of lots of neurons that we recorded from right after the tone was played.
So that's whether or not the neurons are firing more or less?
Okay, so that's where it gets kind of fuzzy. That's why the only way to really say this is there information in that population of neurons, because we don't actually know what that information is. We don't know which neurons need to fire more, and when we don't know if that one's firing more, that means it's probably more.
But you're getting a signal out of your probe, right?
Yeah, we're just getting all of these signals. We're recording all of that data, and then we just input that all into our machine learning algorithms.
Okay. So the signal you're getting out for the low tone as opposed to the high pitch tone, you're trying to see that when you do them one after the other, if the second one is retaining some of the information from the first one
Exactly.
in it? Okay.
That's exactly correct.
And I imagine vice versa also.
And Joel, this would help determine if there is the brain has an understanding, a central clock. There is.
Well, it would actually go to support my PI's theory.
Do you want to go into that?
I don't know if I want to go too into detail about it. I don't really want to risk misrepresenting him in a public forum. But yeah, I'll try to just explain it in general. So he uses it. My PI, Dr. Buonamano, uses a term called neural trajectory. And so the way he says that this population of neurons should be able to, in theory, just inherently encode time intervals. I should be able to explain this so that you can understand it. Sure. Imagine pebbles thrown into a pond. One pebble is thrown, and then 100 milliseconds pass, and then another pebble is thrown. And each pebble is causing ripples. So when the first pebble is thrown, it ripples outwards. The second pebble is thrown. Those ripples are going to either add or subtract, cancel out or add to the think of the height of the ripples.
Sure, interference pattern.
Different points. Yeah, interference pattern, exactly. Depending on what the first tone was, you could, in theory, have downstream neurons that can read out. So now, let's take this back to a neural network. How would that be encoded? If you have a downstream neuron that knows that a specific point in the interference pattern, if there was a tone played beforehand, or if there was a specific frequency tone played beforehand, then it should know to read out a certain amount, and then it will fire downstream. And this is all done with synaptic weights, which enable you to link the neurons, which are the nodes in the network, to greater or lesser extents.
So is what you're saying basically that the time that we experience is somehow in those interference patterns?
Well, it all has to do with being able to read it out downstream. So in theory, if we could, for our research, if we were able to use support vector machines to see if the information is there, then in theory, downstream neurons would be able to read that out. We didn't go look to see if the neurons were wired the way we would expect them to be in order to read that out. We didn't do that, but in theory they could. Does that make sense? So what I mean by read out neurons, the way that would work is have that image in your head of the interference pattern of the pebbles, and then imagine that each of those pebbles is a neuron, and then just imagine that there's a neuron downstream that is connected to those two neurons, and when those neurons are firing at certain amounts, or when the ripples are a certain amount, the downstream neuron either will or won't fire. Sorry, I explained that in the most convoluted way. I'm so
That's
sorry.
okay. It sounds kind of like triangulation, like how we figure out where an earthquake is.
I don't think that it has anything to do with triangulation.
Okay.
But
it sounds like, is there some type of, the neuron that's downstream, is it comparing how it gets information from one neuron as compared to
No,
having
it's
information
just
from the
a
other?
network. I mean, are you familiar with artificial neural networks?
Yeah.
Yeah. So I mean, that's exactly what I'm talking about. Just imagine like the output neurons.
Okay.
The output neurons are the readout neurons that I'm talking about.
I see. Okay.
Yeah.
And those output neurons, that's what will be encoding how we experience time, because that's pretty much what we were getting at, right?
Well, yeah. I mean, if the output neuron can have a specific firing rate dependent on like what the first zone was, then you've got a neuron downstream that's giving you information about time. You've encoded time.
I see. And of course, we're breaking it down to a neuron, but basically the output would be another sub-circuit, something like that, that's encoding all this time. I imagine not a single neuron, right?
Well, I mean, like the idea is basically that all neurons would be doing this, so that it's a fundamental or inherent property of a population of neurons that they can encode time.
Mm-hmm. I see. Robert, what are you doing?
I'm totally just looking at myself. No, I'm kidding. So here's the question. Then, if they can inherently do that, that means that then you've proven that yes, there is a central clock, right? Like,
Well,
so
no, a central clock would be a different.
it would be completely different than that.
Yeah, yeah. A central clock would be something like so the brain has lots of different rhythms
Yeah.
within it, like through the cortex, oscillations, like these neurons light up these neurons, and then it cycles back around, and that might be at 10 kilohertz, I think, or 14 or around there, or maybe it's hertz. But the idea would be that you could keep comparing to that rhythm to figure out where you're at in time. That's
So-
the idea of a central clock.
So if with regard to the study that you
Wait,
guys were doing,
Can I say one more thing? Related
yeah,
to that?
absolutely.
I think the thing with that though is that early theories for any new question that science tries to answer tend to relate a lot to what we know already, or the way we're used to this. So we're used to using clocks. So I think that it's kind of intuitive for the first theory there to be the idea of a central clock, but I don't know if that's the best theory.
I see. So, but you said it was totally different, the central clock thing, right?
Well, you could have both, and I mean, I actually wanted to lead in with this.
Mm-hmm.
The brain doesn't just have to have like one way of telling time. There's lots of different time scales. So like the brain has to be able to tell time on the scale of milliseconds, seconds, etc. And like if I snapped by your left ear. Oh, this is interesting. So if I snapped by your left ear, let's say.
Mm-hmm.
How do you echolocate where that is? Do you know?
Well, it has to do, as far as I know, is that I've heard it in both of my ears, but I've heard different intensities.
No, I mean that would be like a first guess, and that's I think like the intuitive thing that you would think, but that's actually not how we echolocate.
Okay.
It's more interesting than that. It's your brain is processing, or your brain is storing the interval. So the sound is going to reach each ear at a different point in time, so there's a delay.
So one is reaching.
So it's not the intensity, it's the delay.
I see. Okay.
And so that's your brain somehow, and I didn't explain how that's done, but I just said the brain does that, and that's true. And so that's an example of the brain somehow telling time on the scale of milliseconds. The brain also has to tell time on the scale of seconds. Like speech definitely requires being able to differentiate between a second and a second point too, because it can drastically change like the meaning of what's being said. Speech is really complex, so speech definitely requires being able to tell time on the scale of seconds. So there's circadian rhythm, and we're all familiar with that, I think.
It has to do with when we sleep and things like that, right?
Yeah. And so that's
just another, you're saying that's another time scale.
Yeah, it's another time scale. It's another clock in the brain.
Okay.
And there's even ones like longer than that. But my point is that these don't all have to have the same explanation. They don't all have to.
They're not just different settings of the same circuit, basically. They could be completely different systems that are doing
Exactly.
this. Okay.
Exactly. And this science of how the brain stores time is really it's really open right now. It's a really open question in neuroscience.
What scale are you working on? The I guess as a sensory, when you're working on that the one with the ear, the millisecond one.
Yeah, it's like 100 milliseconds. It'd probably fall under the time scale of seconds, like speech.
I see.
Just for speech, yeah.
So if somebody were to ask, I mean, just a layman like myself or anybody out there, if they're listening, right? If they wanted to ask, what is the implication of that? If you guys do all these experiments and you discover something out, what does that mean basically? What would that imply for the rest of us?
Right. Well, hearing aids, helping people hear. I mean, like if we understand like brain science. A lot of times with brain science, you don't really know how. You just got to kind of dig in. You don't really know how it's gonna ultimately impact society or humanity, but I bet you it will.
That's how it is for most science, really, especially physics. Yeah, no one thinks there's going to be that much practical application to most theoretical physics, right? But, eventually you get MRI machines and Velcro and crap like that, and things you didn't expect.
Theoretical physics could save us all one day.
Yeah, hopefully. That's as long as we don't elect Republicans. So I had to bring politics up. I had to bring politics up once. This
we went
this
37 minutes without doing that, and you just broke that. So.
Broke that?
Broke the record.
Oh, is that what that was?
The record was 35 minutes. No, I'm kidding. Go ahead.
No obligatory Trump bashing, though?
No. I'm actually not too sure Trump would shut down science, because if anybody would... Because why do Republicans shut down science? Mostly because of principle. They don't want to, like...
I thought it was money.
Well, they don't want to spend the money, because they don't think there's a benefit to it. And they don't think there's a benefit to it, or they think it's against their principle, like stem cells. However, Trump, I actually think, would invest more in science just because he's a businessman and be like, so how can I get any more of those discoveries that make me the money and the patents and the drugs? So I would actually expect Trump to do more science than any other Republican.
Yeah, I
would agree. It's just a cartoon. Did you see the Stephen Colbert interview?
No, I didn't.
They made like a cartoon. They somehow put him into the show as a cartoon.
That's funny. I'll have to check that out.
It's kind of funny.
I think he would invest. If you told him, you just told what you just said to me, hearing aids. Said helping people hear better. Trump
We'd make
be
the
like,
tremendous hearing aids.
Yeah.
They'd be the best hearing aids that you'd ever see.
Yeah, he'd invest in it.
Trump aids.
Yeah, he'd invest in it.
Trump aids doesn't sound good. That
no,
sounds
it
like
does. Sounds terrible.
Sounds like Trump has AIDS.
Right, but he would invest in it. He would say, "Oh, money. So why not? Let's go with it." Tremendous. I had a tremendous talk with Joel Yancey. He's
the best scientist ever.
He would just talk up a storm. So
all right, so let's rein it a little bit, because I got us off track. So we were talking about how we perceive time, internal clocks, and at different time scales. So let's try to get a little bit more philosophical. Hopefully that doesn't hurt you as a scientist as much as the science has been hurting us as philosophers.
Sure, dude. I think I've lost a lot of people, so
that's okay. We'll get them back, hopefully, with the philosophy, because that's what philosophy does. It brings people in. Wasn't that a popular song? All the boys come to my yard for the philosophy.
Yeah, was that the song? Is that you remembering that correct?
That's how I remember that song. So, how does all this relate to, for example, your research? Can it help us explain why? I think the classic example is if I play a board game with my best friends or something, time flies by. But if I put my hand on the oven, it feels like an eternity type. Mm-hmm. That's what qualia really comes down to. And
wasn't that Einstein?
Does Einstein say that? Einstein compared it to being with a pretty girl.
Yeah.
Versus something. Yeah, but we get
and then something on a stove. I don't know.
Yeah, we get the point. So some things seem like they take a long time. We're in school. We could probably just use that. When the breaks between classes go like nothing, but then being in class takes friggin' forever. Where does that fit into this, if it does, if you can say it all? Not much right now.
Could you reframe that question?
Yeah, why does it seem like fun takes up such little time experientially? Why does it go by so fast when things I don't want to take up a lot of time just keep going on and just feels like it's been forever?
Our experience of time, first of all, there's two factors at play. Or there's just a couple of factors at play here. One is that our perception of time and our memory of time is something you got to keep track of. So a lot of times we might say, like if somebody experiences something that's really horrific, they might tell you that they felt like time was going in slow motion. And they'll tell you that's how they experienced time. But, well, how do you know that wasn't just the memory being distorted? And that actually turns out to be the case. There was some interesting research by David Eagleman, and he actually wanted to test this question. Is time actually being perceived slower when somebody is, say, like really scared? And so how do you test that? He actually figured out a way to do it. And the way he did it was he took his undergraduates out to some really scary theme park ride where you basically like jump off a 150-foot building and you like fall into a net and it somehow catches you and you don't get hurt. But I guess it's basically like jumping off a bridge. And so what he did was he somehow strapped a device to the subjects of the study that would show them, let me see if I can explain this, would show them like a symbol or something that they had to be able to read, like let's say a letter, I believe, and you would have it flashing back and forth with the original image and the inverse, like if you invert the colors. And beforehand, they would have like figured out what the person's. So if you do that, if you keep flipping back between the inverted colors and the original colors, then you could eventually find exactly where if you do it any faster, they can't read it. But if it's any slower, they can.
So is that like working out the brain's frame rate?
Well, I guess. I mean, do you see what I'm saying? Did I explain that well?
Robert,
yeah. So the idea
no,
being that if you're actually perceiving time slower, you should be able to read something that you were just unable to read. Like you just missed it, and like if you're just like in your normal reality.
This sounds like a frame rate,
you
right,
wouldn't
Robert?
be able to read it. It would
that's
just be too fast, like just barely too fast. And so he ran this study, and they found that people couldn't read it. So basically,
time
that
wasn't slowing
doesn't
down
prove, but that's like strong or at least interesting evidence suggesting that you don't actually perceive time as slower. And there's a good explanation for why you would think that you do perceive time slower, like if you experience something horrific. And the reason is we know in neuroscience that the brain encodes memories differently depending on your emotional state. So and that makes sense evolutionarily. Like if you see something really frightening or something really scary happens, you want to encode that memory. You want to remember that for a long time, so it doesn't happen again. And so it makes sense that when somebody goes through something horrific, their brain has laid down a memory trace that contains a lot more details. The brain's not used to that. So then when you recall that memory, the only way your brain knows how to explain that to you, which sounds weird to say, you perceive that as a memory like it happened in slow motion, just because there's so many details there.
So
do you see what I'm saying?
We relate the time scale of our memories to how many details we remember. I mean, that's the way it's sounding to me anyway.
Yeah.
Okay, Robert, does that make sense to you?
Yeah, it's
not actually slowing down for us. We're just remembering more details.
Yeah, exactly.
It's like a trick.
And as we're experiencing something, our brains are storing the memory, right? Like as we're experiencing anything, it's being stored into memory, and then if it's a horrific experience, it's going to be more detailed or less detailed depending on how our brains organize the information.
Yeah. Exactly.
Okay.
Exactly.
Yeah, it sounds exactly like frame rates. Like, Robert, you know how you can tell the difference between slow-mo that's done by just slowing down the reel or by slow-mo that's using a high-speed camera? You know what I'm talking about?
You mean you're talking about film cameras or digital? Sorry.
It doesn't make a difference, really.
I mean,
like if you have 24 frames per second and you want to make it twice as long, right? You want to make it look like slow-mo. You'll just show the frames longer and longer. You'll slow down the image.
Yeah, it'll look different than if you shot it at 48.
Right, it'll be smoother.
Yeah.
Yeah.
If you shot it at a higher frame rate, it'll be because there are more frames going in. There's more physical, and on a film reel, there's more physical material.
Yeah. It almost seems like that's what's happening. We're taking in more detail. Like the time happened the same, but our neurons were saving more details of it, so it looks like it's slower to us when we recall it. Does that make sense? Did I make a proper analogy there?
I suppose.
I
actually had a question that I wanted to ask, totally unrelated, but you study film, right?
Mm-hmm.
What is it like when you watch a YouTube video? What does 720p? What's the P stand for? Because it's not pixels.
It's that's a good question because for the longest time I just accepted it almost religiously.
Yeah.
That was like 720. I thought
I'm pretty sure it was.
I always thought it was pixels, but it's not. Yeah, I don't think it's pixels. You could find it. I don't know, but I do know that you want more than that. But I know on a YouTube video that they put 720. But yeah, I don't know. It's a great question. But this is interesting. So Joel, our experiences. So when people say they perceived time flies when you're having fun, right? When they have a good experience, and
720 horizontal lines. So it's not pixels, but yeah, it's pixels.
Does it actually stand for
Well,
the
that's
P
that's not what a pixel is.
I know it's not
I mean,
what
like
a
the
pixel.
way
That's because
TV
you're
screens work,
you're
you've got,
thinking
like,
of a.
horizontal lines and you've got vertical lines. I mean, I don't really know how this works, but it's not pixels.
It's not pixels technically, but this is a terminology for a television, and you're talking about how it's used online, so that's why it gets confused. For a television, it's basically a pixel. It's a number of lines versus number of columns on the television screen. So that is just used as a shorthand for quality when it's brought over to. So I say, what it was recorded in? It was recorded in this many rows and columns. So it essentially is pixels, but it's not a pixel.
There's a reason why it applies to video. Like, you've never seen a picture with a P, like this picture is 720p. You've never seen that. It has something to do, I think, with like the frame rate or something.
No, it's not. That's what it is. The frame rate's totally different. It also has to do with the aspect ratio. Robert, what were you saying?
I was asking so when people say things like time flies when you're having fun, so they have a really good experience, and they're like, it felt like that was a 3-hour experience, but it felt like 15 minutes, versus the other when they have a 1-hour experience and it feels like eternity. So that's basically just our brains kind of storing memory, and are they just misinterpreting, or they're just recalling memories, and those memories are feeling like they were longer or shorter, faster?
Yeah, I mean, this has been like touched on by neuroscientists before. It's been variously described as, or termed, the holiday paradox, actually.
I like paradoxes.
So, but yeah, it's just as I described it. So
that is the paradox?
How much time do we have left?
That's a boring paradox. We have 12 minutes left.
Right.
You want to move on to AI?
Certainly.
Yeah, let's do that.
I always want to move on to AI.
So you talked about it briefly by saying you use that type of machine learning algorithm, right? You want to start by talking about that?
Support vector machines. So we didn't use them directly. We used them indirectly to, like, our research wasn't related to the algorithms. We didn't write the algorithms ourselves. We just used them in MATLAB. We used a library called libsvm.
Oh, you used MATLAB? That's funny. That's where I used AI also.
No, we didn't use MATLAB. We used libsvm.
Oh, okay.
So, it's...
So what did the machine learning do for you?
Well, we used the machine learning to... I'm just going to keep trying to explain this the same way. We used it to see if there was information in the neurons.
Right. But how does it do that? What does machine learning mean?
So I wish this was a video podcast because I could show the...
we can always put a link up.
We'll put a link up if you do.
Do you have my poster on there?
No, I don't.
All right. Well, we used the machine learning. Okay, so just give me a second to like collect myself, and I'm going to explain this.
That's fine.
I'm going to explain it well. No, I can explain this. So, like, you remember how I explained the experiment? So
yeah.
You've got the 3 different conditions, like let's say you've got low pitch tone, high pitch tone, and noise, and we've got data for the brain activity lots of data for the brain activity for each of those conditions. We train 3 weight matrices. We train 1 to recognize each tone, and then we do like a winner takes all. So whichever one has the highest output through the test data. So you know how like machine learning algorithms work, right? Like you have like
should explain for Robert too, though.
Yeah, especially so
that sounded
machine
mean.
learning
Sorry, Robert.
algorithms
No,
can
it's
be
fine.
like divided
I'm
into
used
2
to it,
camps, supervised and unsupervised. And supervised machine learning algorithms, you get to have like test data. So you get to have training data. So you get to train the system with some of the data, basically. So
then you could see how what the training results into, like.
Well, no. So we can make these weight matrices that are trained to recognize specific tones.
The way I understand it is that you have this certain algorithm that has an input and output, like any other algorithm, and what you're trying to do is train this algorithm so that when you put in a range of inputs, it gives you a specific output. Does that sound?
Not a range. Why do you say a range?
Well, for vision learning, you have to make sure that it recognizes a person in the many permutations it can come in, because a person can be in many different shapes and forms, but it has to recognize them as that same person in all those different inputs. Does that make sense?
Do you mean like a face from a different angles? Like seeing the same face from different angles?
Yeah, that's exactly what I mean. So, I mean, the input can be the same face, but it could be at different angles, intensities, or sizes.
So when you use the testing data to see how accurate or how much information is there, essentially, you're going to get good results if the testing data is is very similar to the training data.
Well, I don't know. I'm not that well versed to say anything about that because I think I'm confusing myself about what it was. I just know that that's how we used the algorithm for is so that. I mean, basically just how Robert said it. You don't just want to recognize a face because that's a specific set of pixels, but the face can be rotated, it could be stretched, it could be lighter. Or
So you're talking about kind of like image processing.
yeah, that's how I used it was for image processing.
Yeah, I think that what I was trying to describe was confusing enough. We don't need to bring in image processing.
Sure. Okay, but that's as far as I know about it. So, but you used it differently then.
Well, we just used the support. I'm just gonna keep saying this. We just used the support vector machines to see if there was information in those neurons.
Yeah, no one knows what that means.
So I guess I failed today.
That's okay. Well, let's get to something more interesting then. Let's talk about.
And it is confusing. So
that's okay. I mean, some of the most hardening
I don't think I'm
coding anyone could do.
Yeah.
As far as AI goes, we could just go and talk about like sci-fi type AI. I mean, do you want to go ahead and talk about that?
Did you see Ex Machina?
No, I didn't yet.
I did.
I highly recommend it.
Yeah, I loved it. I don't know anything about the science behind it, but I thought it was a great movie.
I'm sure it was
totally.
shit science. It's a movie.
No,
so.
yeah. There's no science in it. But
Robert and I argue all the time about how movies
But
fuck
it
up
was-
science.
But it
very
didn't
well
matter
written, great
because it
plot.
was a great movie.
yeah.
How
it
would
was
you
very
know? You
well
think
made.
bridges float?
Yeah.
This is an ongoing argument.
What was the one robot's name? The Asian one, Kyoko.
I think so. Yeah.
Yeah, she was the spy.
Yeah, no,
Spoiler
I
alert,
guess-
What the
I
fuck?
think.
Quit
I guess-
spoiling. Jesus.
I
shit.
Well,
guess.
it's a theory.
Yeah.
I mean, like, I don't even. You know why I think that is like there's one little snippet where she like.
No spoils. No talking about the movie.
Can I ask
Talk
what you?
after the
You
show.
should have seen it.
Can
I
I
should've
ask what
seen
you
it
what
by
you
now.
liked about the movie overall?
Sorry, what's that?
Can I ask what you enjoyed about the film overall? You don't have to, like James saying,
We could
spoil
pick a different movie. There's like
Oh.
1,000 different AI movies.
Yeah, it was just I thought the writing and stuff was really good. Like
Okay.
I didn't think like the AI was like super informative or enlightening or it didn't make me consider any new philosophy or
Okay.
anything. But
So,
That sounds like failed sci-fi.
it's just a good movie that happens to be about something that I'm interested in. It's
There you
funny
go.
how that happens, isn't it?
So let's talk about. First of all, there are a lot of philosophers who think AI itself is impossible. As a scientist who works specifically with neurons and how the brain works, what do you think about that?
No, I mean, well,
No, is it should be possible? That they're wrong? Is that what you're saying?
yeah, I think it should totally be possible.
Okay. They said.
I mean, like on one extreme, we could basically build something identical to a human brain, but it wasn't ever born, But so it's like, how different can you be from that, and to still get something that functions in the same fundamental way as the human brain? I mean, I'm a reductionist and a physicalist, and I think that the way that the human brain works is something that could totally be recreated, and it could. And I think the really interesting question is how different from the human brain could something be to still be, what we call conscious. And I'll try to use the word conscious as few times as possible.
That's fine. I think the one way I agree with a lot of philosophers and things like that is that machines work linearly, and our brains simply do not. There's not like a CPU.
what do
in
you
our
mean?
head.
What do you mean by that? They
A
work
computer does one as fast as our computers have become. They still, at their core, pun, do one process at a time. They'll do one addition, one subtraction. They just happen to do it trillions of times a second, so it looks like they're doing lots of things really fast. Well, they're doing lots of things really fast.
Let's be clear here. Like we can compare machine learning or AI or artificial neural networks to the way the brain works. Like we can make those comparisons, but it's not a good comparison to talk about like how a computer, how a typical laptop works compared to the human brain, because they work on fundamentally different principles.
That's what I'm getting
And this
at.
is worth pointing out because a lot of people think that might be a natural analogy, like, your laptop's like a brain, but it's
Yeah.
not. It's very, very different, and I think people need to know how it's different. It's because the brain works. The brain has an associative architecture. That's the best way to say it.
Okay.
So concepts, ideas. It doesn't matter. Memories. The more closely related they are to each other or similar, determines their. That's how they're connected.
Right.
So the brain associates things. That's what you're
It's
saying.
an
That-
associative architecture. Let's just say I said that and didn't try to elaborate on it.
okay.
Which you didn't. But yeah, that's exactly what I was saying. They're fundamental. So when the philosophers say things like AI is impossible for a computer, it's because of these differences we're talking about. So it almost sounds like you agree that AI could be impossible for that type of architecture. So if we want to make the type of AI in these movies, like Ex Machina, we'd have to come up with a fundamentally different type of computer. It wouldn't just be CPU plus RAM plus hard drive.
Yeah, well, it would have to use some type of machine. I mean, it could use artificial neural networks, and I think if that was done in the right way, then yeah, we could create a conscious machine. One more catch, though, is that the brain isn't just setting up a network or an artificial neural network in the right way. The brain has also got a lot of very specifically designed components that are linked in really complex ways. You know, like you can't even separate the sensory systems of the body from the motor systems completely, because you've intrafusal fibers and your muscle fibers. They're all linked. Like there's sensory receptors inside your.
You're saying neurology
your
is
fibers.
Complicated.
I'm saying that the systems are linked.
Right.
So how much does that relate to what we value as consciousness? Come from like that modularity and the intricacy in that, you know.
And as much another interesting point, as much as they're linked, I find this interesting. I forget what's called, like a hemispherectomy or whatever it is. If there's someone who's having horrible seizures in one part of their brain, one of the more drastic surgeries would literally just take an entire hemisphere out of their brain. Yeah. And a lot of people would think, well, isn't that just going to make him, stupid or whatever, a vegetable? It turns out the other hemisphere will just relearn whatever the previous
really
one
bad
needed
epilepsy,
to do.
I think.
Yeah. So you could actually live with one hemisphere of your brain.
Yeah, totally, and you can be fairly normal too. Yeah. People are surprised. Yeah, the brain is very malleable.
What is it called? I was going to say elastic, but malleable. That's a good word. Yeah.
The brain is very good at figuring out what inputs it needs to take in and producing an output that works.
Right. The brain's pretty cool. What was that quote I sent you? I used to think the brain was the most important organ ever, and then I realized what was telling me that. That's Emo Phillips. Good,
it's
funny
plankton from SpongeBob hiding inside your brain, controlling you.
I have no idea what that means. I'm really old.
You never watched SpongeBob?
That's beyond my time. Sorry.
Damn it.
Tell me in Animaniacs.
I watched that too, but I don't think I could link this one.
Pinky and the Brain?
Yeah, Pinky and the Brain. There you go. Brain.
All right, so that's about all the time we have. I want to thank our guest. Thank you very much for coming on. Did you want to briefly say who you are and what you do again?
Well, thank you for having me on. My name is Joel Yancey, and maybe I could end with just something in neuroscience that I find really cool.
Sure, go for it.
Something that I find really interesting is the placebo effect, and I've got a little quote here from my textbook, actually.
Okay, and it's on the placebo effect. So for those who don't know, the placebo effect is when you do a test on a drug, you'll give half the group people the real drug and half the people sugar water, basically, to see how much thinking getting the drug actually helps or how not having the drug at all helps. So test measure.
I don't know how you do that off the cuff like that. Well explained. Yeah, so I don't know if you guys ever thought about it, but the placebo effect, if that's an effect that's detectable, you're not detecting nothing. You're actually detecting a real thing. So like the placebo effect has to be in some sense a real thing. You know,
that's what I always wondered. Same. Yeah, I always wait, but if it is producing some kind of result in the body, isn't it a real effect in itself?
Exactly, it's got to be. So let me just read this quick quote. It's just one sentence or two sentences. Although the mechanisms by which the brain affects the perception of pain are only beginning to be understood, the effect is neither magical nor a sign of suggestible intellect. In short, the placebo effect is quite real. And I think that's pretty profound.
Yeah, I think that is fascinating, actually.
All right, you've been listening to UCLA Radio.com. Let me enunciate my words.